Today I'm joined by Dr. Emily Rickman, an astronomer with the European Space Agency based at the Space Telescope Science Institute in Baltimore, Maryland. The Space Telescope Science Institute is the home of mission and science operations for both the Hubble Space Telescope and the James Webb Space Telescope. Emily studies exoplanets and brown dwarfs, directly imaging and characterizing distant worlds. She's also involved in telescope operations and instrumentation for some of the most powerful observatories ever built. Emily, thanks so much for joining me.
Thank you so much for having me. I'm excited to chat today.
So, before we get into the science, what is the European Space Agency?
Yeah, so the European Space Agency, or ESA for short, is basically just the European version of NASA. So many people will be familiar with the US Space Agency that is called NASA. But the European Space Agency consists of many different European member states who all sort of contribute different amounts into a European-wide space agency. And then we have our own space program where we launch our own missions, our own telescopes. And then a lot of the work also happens in collaboration with international partnerships. So ESA works with NASA and the Canadian Space Agency, also the Japanese Space Agency, many others. And we launch missions together sometimes. So the reason that I am based here in the US, in Baltimore, is because the European Space Agency is a partner in the Hubble Space Telescope and the James Webb Space Telescope missions. So that's basically part of what the European Space Agency does.
So, the Space Telescope Science Institute, that's where you're located now.
Yeah.
What else is happening there?
Yeah, so it's a bit of a mix between science and engineering. So we
Okay.
have about 800 or so staff members in total. About 200 to 300 of those have some kind of science or research time. So sort of similar to having academics at a university that spend time doing research.
Yes.
So like myself, like we spend time sort of working on different topics in astronomy. And then we also
Okay.
have a large number of engineers, software developers, people who support the missions in that way. And then a lot of technical staff who help with the operations of the James Webb Space Telescope and the Hubble Space Telescope. So we're like a large cohort that kind of do somewhat science and mission operations. And then we also do a bit of science and research as well. And we're affiliates with the Johns Hopkins University. So we're on the campus of Johns Hopkins. So we also have
Oh,
graduate students and postdocs who work with us who do a lot of the science research as well.
oh, nice. So, the Hubble Space Telescope, it orbits Earth about 340 miles above the surface. Why is it in that specific location? Like, why 340 miles?
Yeah, so Hubble orbits where it does because it's what we call low Earth orbit. So it's close enough to Earth that we can communicate with it pretty easily and downlink a lot of the data that is taken. So there's large data volumes, and so we can kind of pretty consistently get that data from the telescope to us on Earth. And then that kind of resets and we take more data. And so it's kind of good from that perspective. Also, in terms of like launching it, it's pretty easy. Wasn't always easy, but it's pretty easy to launch things into low Earth orbit. And then the other part of Hubble as well is we wanted a serviceable mission. So
Oh,
one of the concepts with Hubble was being able to send astronauts to the telescope to make upgrades over its lifetime. And that was part of the space shuttle program, which has since decommissioned. But during the sort of early 2000s, people may remember the space shuttle did a large number of launches, and some of those were to Hubble to make upgrades to our instruments. And so that's a pretty unique capability to exist in that low Earth orbit and actually be able to send humans there and make upgrades.
so it's almost like this sweet spot. Has it been in that location for a long time?
Yes, it
Okay.
has. It was launched into that location. It has lived there for more than
Oh,
35 years now.
wow.
So it orbits around Earth. So you can look up where Hubble is in its current orbit, and there are
Yeah.
times where you could even see it orbiting overhead, no matter where you are on Earth, pretty much, because it sort of
Mhm.
precesses around Earth. But yeah, it's been there, and we do have to deal with some effects of because as even at the point it is in space, we still have some small like atmospheric effects from Earth because the atmosphere doesn't just cut off at some point. It sort of gets more and more diffuse.
Oh, yeah.
And so there is some drag that's caused from the like upper atmosphere where space kind of begins. And so we do have to deal with some drag over time that it kind of gets a little bit lower in its orbit over very like long time scales. Um,
Okay.
But that is something that we have to take into account in low Earth orbit as well.
Okay. So the James Webb Space Telescope
Yeah.
operates at something called the second Lagrange point, or
Mhm.
L2. Hopefully I'm pronouncing that correctly. What is L2?
Yeah, so as any celestial body, so like planet Earth, for example, orbits around the sun, we have these points that trail sort of with respect to Earth. So there's kind of a Lagrange point in front of Earth, behind Earth, and sort of away from Earth with respect to the sun. So you imagine there's sort of different quadrants if you were
Okay.
to look out away from Earth. And those are what we call sort of gravitational stability points. And they're basically points that, because of the way the gravitational field is shaped, you could put something at that point and it wouldn't really move with respect to Earth. So if you,
Oh,
it kind of moves with Earth. So it's as Earth orbits the sun, that Lagrange point or gravitational stability point basically orbits at the same time as Earth. So it's very handy for us because we can kind of put things there and they kind of, it's like having like a trailer that you're kind of like dragging along with you. Um, so
oh,
we have to make slight adjustments over like periods of time, but like it's more or less a stability point where we can put satellites and telescopes and use that.
interesting. And in 2021, that's where it was intended to go.
Yes, yeah.
Okay. How long to get there?
The actual journey time is like a matter of days.
Oh, days. Okay.
Yeah, days or weeks of that order.
Okay.
But then we have a commissioning period when we launch these things. So what happens over the like first few months when we launch this is we're not in science operations immediately. We have this commissioning phase where we're trying to understand like the instrument like on board and deploying the telescope. So it just kind of gets launched and then as it's kind of traveling towards the Lagrange point, we start doing those commissioning activities. So some of them happening as they're traveling, which is why I'm
Oh,
like trying to think what the actual journey time is because a lot of these things happen in parallel. So once
I
we're away from the orbit of Earth, then we can already start doing some of these activities. And then that happened over a period of 6 months. But we weren't traveling for that entire time. But
see.
the actual full commissioning period, including travel time and including deploying the mirrors and the sun shield and everything else, took about 6 months.
How big are these telescopes?
So the James Webb Space Telescope has a mirror diameter of about 6.5 meters or 6 meters. And then the Hubble Space Telescope has a mirror diameter of about 2.5 meters. So James
Okay.
Webb is significantly bigger and it has segmented mirrors in hexagonal shapes. So we can actually adjust the shape of the mirror and make sure it's like as focused as best as we can. It also means that we were able to launch such a bigger mirror because it was folded down inside of the launch vehicle when it was launched and then it was deployed afterwards.
I see. How do you communicate with these telescopes?
Yeah, so the James Webb Space Telescope use what's called the Deep Space Network, or DSN for short, and that consists of three large stations across Earth. So we have one just outside of Madrid, one in
Mm,
California, and one in Canberra, Australia. And so at all times, like no matter what way Earth is facing, we're able to communicate with James Webb if we need to. And not just James Webb, but also there are many other satellites further out in the solar
okay.
system that use the same deep space network. So we're connected to the DSN for 8 hours a day, more or less. So
Oh,
that is a significant fraction of the DSN time. And because it's the largest, most powerful telescope, we need that time on the DSN in order to downlink all of our data. And so a bunch of data will be taken and then over like 24-hour period, and then there'll be a downlink time where everything is getting downloaded while it's still able to observe as well. So that's kind of when we like reset the memory on board the telescope in a way. And then yeah, other big telescopes and missions use the same deep space network. So we can run into scheduling difficulties sometimes when we have crewed missions, for example. So the Artemis launch is about to happen to the moon, and they have priority on the deep space network because they have
oh,
humans on board that need that communication. And
right.
so we have to adjust our schedule around that a little bit, but we can
I,
anticipate that ahead of time.
okay. And what about communication with Hubble?
Hubble is much easier because it's so much closer to Earth, so we can actually
Yeah.
just directly downlink from Hubble, which is one of the pros of being in low Earth orbit. So
Yeah.
we can kind of do that on a regular cadence as Hubble is orbiting over our ground stations that we use to downlink the data.
Oh.
The reason we have to use a deep space network for James Webb is because it's so much further away, so we need the strength from those ground stations in order to access the data. But because Hubble is so much closer, then we don't run into those same issues.
What are each of these telescopes used for? And also, how far can they see?
How far they can see is a really difficult question to answer because they can reach as far as we want to stare. Like if we spend an infinite amount of time on the telescope
Right.
staring, then we would be able to see to the outer reaches of the universe. So like almost 14 billion light years away.
Hubble as well?
Yeah, yeah.
Oh, okay.
And so the big difference between Hubble and James Webb, beyond the size difference, is one thing, but they're doing quite different things because they observe in different wavelength ranges. And so
Okay.
Hubble observes in the ultraviolet or the UV and the optical wavelength range, whereas the James Webb observes in the infrared. So those wavelength ranges are much longer. And we're seeing different astrophysical phenomena at those different wavelengths. So
I see.
UV optical usually corresponds to much more high energetic events, because those are more high energetic uh, uh, like particles that we're seeing and effects of those energetic events. Whereas in the infrared, we might see things that are much colder that we're just not able to see in the UV. We can see
Okay.
through different phenomena like clouds, the interstellar medium. And so we're just looking at different things. And the real power is having both of those telescopes and looking at the same astrophysical thing, but across all of those wavelength ranges. So being able to observe with both Hubble and James Webb simultaneously is really powerful, or being able to put that data together and kind of stitch it together and get a more full understanding of the things that we're looking at.
What do you mean when you say the longer you look or the longer you see, the further you can go? Like, what does that actually mean?
Yeah, so the longer we can stare at something and then we can get the photons that are traveling from, let's say, a distant galaxy will arrive at the telescope, and then we're able to pick
Right.
more of those photons. So basically, a telescope acts like a bucket in a way of photons, and photons are the things that we're seeing. Those are the things that interact with our eyes or a detector, and then
Right.
we can convert that into an image or a spectrum or something that means something to us that we can interpret. And so, because some things are so distant and so faint, we just need the amount of time to actually collect enough photons to be able to
Right.
actually see what is happening.
Okay.
And so those really, really distant faint things just need a lot of what we call integration time to be able to really look that far away.
So these telescopes are consistently looking, right? They're always on. So does that mean that they're essentially seeing further and further away as time goes by?
Not, I mean, they're always looking at different things. So,
Right.
like, we try to push the boundaries of what we're
I
seeing,
see.
and some observing team may decide to try and push that boundary and look like even
Oh,
further
okay.
away in a sense, but they're not always staring at the same thing. Like we're constantly slowing, we're constantly
Yeah.
re-inquiring on new targets and looking. Like a lot of observations may just be 30 minutes or an hour of
I
observing.
see.
And so we're constantly changing what we're looking at in the sky. We're not just staring at one thing.
So if it was looking in one direction at one thing for 6 months, you might see something interesting in a different way than using it for specific research or studying specific things, which is how it's used now.
Yeah, and that I think would be amazing if we could do that.
Right.
But yeah, like from a resource perspective, that would be very tricky. But we've done like smaller scales of that before where we have just taken a large chunk of time to just stare into a piece of the sky that no one had previously looked at in that much depth before and found
Right.
quite surprising things. So we call these like deep fields, that Hubble and both Hubble and James Webb have looked at in different ways.
What's a surprising thing that you saw?
So the Hubble Deep Field is really was one of the things that kind of made me super excited to get into astronomy when I was younger. And so I think it was just surprising to astronomers at the time. I was pretty young when this happened, but of just that what we thought was a really dark area of the sky that didn't have too much exciting activity happening. Actually, when we just like sat and stared Hubble for many, 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 many hours across, I think it was days, where Hubble was just staring this patch of sky. We saw as a result, like all of these dots, all of these different components that all turned out to be different galaxies and a huge different
Oh, wow.
variety of galaxies, like different shapes, different colors. Um, it really just changed our perspective of the sheer volume of galaxies that exist in the universe, and also like how far we're able to see, and our understanding of like the expansion of the universe as well. So I think it really opened up sort of a new subfield in a way of astrophysics and how people perceived what we're looking at.
So what does your job at the Space Telescope Science Institute actually entail? Like, what does your day-to-day look like?
Well, no day is ever the same, which is
Yeah.
great. But yeah, so I spend half of my time doing scientific research. So I supervise postdocs who do a lot of the science that I work on. I run a program that we're specifically looking at the atmospheric properties of exoplanets using the James Webb Space Telescope. And so that's like half of my time is like doing research. So analyzing data, writing code to analyze that data, writing papers, publishing scientific
Mm.
papers in journals. And then the other half of my time is spent supporting the science operations. And I actually work on both the Hubble Space Telescope, specifically on the STIS instrument, and then also work on JWST on the MIRI instrument. And so we have different aspects for operations, but we do things like user support. So if you are a principal investigator on a program for either James Webb or Hubble, you will have someone assigned to you that's called contact scientists. And we support those observations in making sure that everything is set up that you need to do your science case. If we find any issues or resolve any problems you may have with setting those observations up or getting the data. We also help with calibration. So we regularly take standard like calibration. So we'll look at the same star over like many, many years, for example, to make sure that the telescope is behaving as we expect it to. So if we see
Oh,
any differences in um, like the shape of the spectrum we might see or the amount of light we're receiving from that star, then like that could indicate that there's something happening with that instrument. And it's important that those calibrations are taken regularly so that the people who
uh,
use that data are getting the best data possible. There's also things like the pipeline that we use. So this is the how the data is produced and analyzed. So how we go from what is sent to us from the telescope into real scientific products that can be used for interpretation in the community. So science operations is a very sort of
mm.
large encompassing term of like many different axes that we work upon, and that are very important to the astronomical community.
So how does scientists get to use the telescopes? In other words, do they get dedicated time to use the telescopes? And do they have to write a research proposal? Do you review those? What's the process?
Yeah, so actually anyone can submit a research proposal to
Hmm.
use the Hubble Space Telescope or the James Webb Space Telescope. You don't have to be a scientist, but it's extremely competitive.
Yeah.
And so we're very much oversubscribed. What happens is once a year, there will be a deadline, a separate deadline for Hubble and James Webb. And astronomers and people from all over the world can submit a proposal to basically say, I would like to look at this object or this series of objects that
Mm.
I'm interested in order to do this science case. And the review process really takes months, actually. And so, like the last cycle for James Webb Space Telescope, the proposals were due in October. We're now in the end of February, and we still don't have the results of that because it takes so long to do the review process. We should have them in the next few weeks. But so it's a really intensive process. We basically collect astronomers from all over the world who become part of the review
Oh,
process. And
I
we
see.
have panels that target different sub areas. So we kind of split the panels into different levels of expertise. So someone might be, a panel might be an expert in galaxies, a panel might be an expert in planets, for example. And we have so like lots of different panels that work together in parallel. To review the proposals. And then they end up ranking them and suggesting, like, we think these ones should be observed within the allocated time. So the cycles
Mm.
happen on a yearly basis. And then we have to allocate, like, within the time allocation that we have available, sort of put all of those proposals together and make an observing program. So it's a pretty intensive process. It's very oversubscribed.
Yeah.
Yeah, we spend a lot of time writing these proposals to kind of formulate the best hypotheses that we can to say, okay, how can we answer this science question?
So you study giant exoplanets. What's an exoplanet?
Yeah, so an exoplanet is just basically any planet that orbits around another star. So much like we have planet Earth, or maybe a planet like a gas giant like Jupiter that orbits around the sun. Almost every light that you see, the little dot in this that you see in the sky is another star. And around that star, statistically speaking, is likely to host a planet. And that planet we would just call an exoplanet.
How many are there?
So far we've discovered more than 6,000 exoplanets, but there are many more than that. We believe that almost every star, or the vast majority of stars, at least within our galaxy, host a planet. So, like, there's many, many, many more to discover, but
Yeah.
the field of exoplanets is still relatively young. And so, yeah, 6,000 so far, but I think that number is going to boom into a much higher number.
And then do they vary in size? Are they all completely different? Are there similar exoplanets?
Yeah, there are all kinds of different planets. So much like in our own solar system, we have different planets. We have rocky terrestrial planets like our own Earth and Mars, and Mercury and Venus are sort of rocky and much smaller in nature. But then we have like gas giants like Jupiter and Saturn and Uranus and
Mhm.
Neptune. And so these are kind of different, what we would call families of planets that have different compositions. And we see some of those different families in exoplanets as well. We also see families of planets that we weren't expecting to discover. So, for example, super Earths, which are similar to Earth in that they're terrestrial in nature, but they're much more massive than our own Earth. And so, those were kind of a surprising subfamily of planets that we discovered. Um, Things like hot Jupiters, so much like our own Jupiter in the solar system, but instead of being in the outer reaches of the solar system, these ones orbit very, very close to their host star. And so
Okay.
instead of being like a cold gas giant, they're a hot gas giant, hence why we call them hot Jupiters. So
I
there are many different types of exoplanets that we find, and we're trying to comprehend like what those different types of planets mean and how they all formed and ended up in their different places.
Why is it important to actually study exoplanets?
Yeah, I think like there's some philosophical component here, right? Where
Okay.
I think a lot of people throughout history, throughout millennia, have looked up to the night sky and wondered what's out there and what our place might be in the universe. Planets is a part of that. Like it's been pondered for a long time that there would be some other planet around some other star. And it wasn't until more recent times within the past couple of decades that we're actually able to observe these for the first time. And so much like even in ancient time, people would try and understand the stars in our night sky and start trailing out the planets within our own solar system. I think it's a similar part of that where it's just like, what is our place in the universe? How does the universe work? How do the universe
Mm.
laws of physics apply to the same laws of the universe apply here on Earth as they do in other places in the universe. And so to try and understand that on a much wider scale, I think is a fundamentally important thing to do. A lot of astrophysical research has then ended up having implications more that are more broadly applicable across other areas of what
Mm.
might impact our day-to-day lives. But I don't think that's like the primary motivator for doing it, but it is an important side aspect that comes from technology development in order to do our research.
When was the first exoplanet discovered, and how often are you discovering new exoplanets?
Yeah, so the first exoplanet that was discovered around a solar type star, so a star very similar to our sun, was in
Yeah.
1995.
Oh.
And this was discovered by Didier Queloz and Michel Mayor, who won the Physics Nobel Prize in 2019 for their
Mhm.
discovery. And it was the reason that I actually studied my PhD Geneva Observatory, because that's where they're based, and were the founding fathers of the field. So
Mm.
only a little over 30 years ago now that the first exoplanet was found. And so that has increased in the rate that we've been able to discover planets. So when the first planet was found, it was very sort of slow and incremental because people were being like the technology available is different to what is
Mhm.
available now. We've had a lot of advances, but also being very cautious and careful of like, is what we're seeing truly a planet? Could it be something else that is like masquerading as a planet? Whereas now we have huge advances in technology that allow us to look at lots of different stars with lots of different telescopes simultaneously around the world. And so, like, I remember when we reached hitting like the 1,000 mark of planets. I think in like 2000 and maybe like 2010 or 2011, something around that
Oh, wow.
time. And then we've gone from that in like, let's say 2011 to like now we found 6,000. So the rate at which we're
Wow.
finding planets is increasing all the time. So like it went from if you found a planet, that was like a huge deal to now like, okay, great, like we found more planets. But the field has transitioned more from not just finding planets, but truly understanding the planets that we look at. And that number is going to boom even more as well. We're about to launch another space telescope this year, and
Mm.
we anticipate that we will find tens to even hundreds of thousands of exoplanets in the coming years. So it's just going to keep increasing potentially exponentially.
So you do all this research studying exoplanets. What is your main focus? Is it discovering new exoplanets? Is it researching specific exoplanets and the ones that are, like you said, they're terrestrial, they're similar to Earth? What's your main focus?
Yeah, so right now I am mostly excited about planets that are more similar to gas giants, so more similar
Okay.
to Jupiter. And I really love looking at their atmospheres. So we've, like I said before, we've kind of transitioned a bit from detecting and discovering exoplanets, which is still fundamentally very important, but actually probing now the planets that we do find and actually really understanding those properties. Like,
Right.
thanks to the technology of the James Webb Space Telescope, we have access to a spectral resolution and sensitivity that allows us to look at the atmospheric properties of these planets in a detail that we were not able to do previously. And so that's what I'm very excited about nowadays is trying to understand those atmospheres.
Is there like a, I want to say automated, I don't know if that's the right word, a more automated process for detecting new exoplanets since we've detected 6,000 of them already? I think that's a big number. And maybe compared to how many there are, it's probably not that big. But like, is there just a like an automated process for detecting exoplanets within space that can almost send alerts to the team? Like, hey, I think we've detected something that looks like an exoplanet. You may want to investigate further.
Yeah, so there are aspects where we've tried to move in this direction. One of the things to note is that a lot of the exoplanets we find are not all through the same detection method. There are many different ways to
Oh,
find exoplanets. And
wow.
so
Okay.
it's not a homogeneous way of looking across and how we're doing this. So it depends on the morphology. There's also things like telescope resources that we're not just aimlessly staring at the sky and hoping that we find detections. Like a lot of telescopes are very targeted in that
Mhm.
they're looking at a single object to try and take specific data to see if that one star hosts a planet. And it can take a lot of intensive time to do that. But this is going to change. So I'm kind of glad that you brought this up because the Roman Space Telescope that I mentioned that's going to launch later this year, which will be our next big space telescope, has an extremely wide field, much, much bigger field of view than what we can see with Hubble. And because it
Oh.
has such a wide field of view, we're going to be able to look at lots of stars at the same time, which is something that Hubble can't really do. And so it's very complementary to Hubble, but because it can look at lots of different stars, we hope that we'll be able to detect many, many more exoplanets in a more, I don't want to say automated, but in a much more sort of homogeneous way than we've been able to do previously. So we've had smaller missions that have done something similar. So there was the
Mhm.
Kepler space mission that was launched in the 2000s, is no longer in operation. But Kepler was responsible for booming the field of exoplanets, and it found a couple of thousand exoplanets, which at the time was a huge increase in the number of planets. And it was thanks to the fact that the telescope was just staring at a field of stars over a long period of time. So we were able to
Mhm.
detect many at once. And then there was sort of a follow-up mission to that called TESS, TESS, from also from NASA. And TESS is still in operations. And it's sort of similar to Kepler in that it's able to look at many stars and find more exoplanets. But Roman is going to have an even wider field of view that's going to be able to do this on a much larger scale. So I think this is going to be the next boom in the number of exoplanets that are detected.
Interesting. What are brown dwarfs?
Yeah, so brown dwarfs are something that sort of is between what we would call an exoplanet and something that we would classify as a star. And so they're often called failed uh, stars in that they're not as massive as stars, but they're much bigger than planets. And so they're kind of in this intermediate mass range. And the
Mm.
reason that we love them, or the reason that I love them, is they have very similar atmospheric properties to giant planets, but they're much easier to see because they're much more massive, they're much more luminous, and so the amount of light, the amount of photons that we receive from them make it much easier for us to investigate in a level of detail that can be harder to do at the planetary mass regime. And so, yeah, they never quite got massive enough when they were forming to go into full fusion to generate light like a star does, but they are much more similar in nature to planets, but potentially formed like a star. So they're this sort of intermediate object.
Why are these important to study? Other than you're fascinated by them?
I mean, they're important to study as they're part of like our spectral classification of understanding all of the stars and celestial objects in the sky. We have a lot of brown dwarfs, like they're very high in the number of them that exist. And so trying to understand their properties and how they formed and evolved is very important. And some of them orbit around other stars, so they might be a bit more similar to planets, but some of them are
Oh,
also isolated, and we call them field brown dwarfs, and they kind of hang out by themselves like some stars do. And so trying to understand like the nature of those and the fundamental differences, I think is pretty important. And then, as I mentioned before, using them to help probe and understand atmospheric properties of giant planets at play is another important aspect of what we can use brown dwarfs for. And yeah, and it's also been suggested that brown dwarfs could make up some of the what we call dark matter in the universe.
oh.
I don't know if that is actually the case, and I think that's a large outstanding question. But understanding the number, like statistically understanding how many brown dwarfs there are, is also kind of an important fact on a broader cosmological scale as well.
How many have been identified?
Oh, like tens or hundreds of thousands. I
Oh,
don't
okay.
know the exact number. Many
Yeah, okay.
more than I would know. Yeah.
So I imagine you have all the exoplanets like labeled and named. Like, can I see a map of all exoplanets online? Is that something that I could find?
Yeah, I think if you go to the NASA Exoplanet archive,
Oh, okay.
they have a lot of information that you can check out on there. You can make lots of different plots depending on what you're interested in.
Oh,
I think they have like 3D animations where you can go in and see what the orbits of those planets look like. And
I see.
yeah, but that's a really great resource to check out. Yeah.
Is it the same for these brown dwarfs? Are they all mapped, like named, labeled? Is that publicly accessible data?
Um, I will say there's not as nice an archive for the brown dwarfs as there is for exoplanets.
Yeah.
Some of these brown dwarfs are close in mass to what would be considered a planet. So depending on
Okay.
who you ask in the field, some of these brown
Oh,
dwarfs may exist also on the exoplanet archive, because
oh,
we have
interesting.
like uncertainties when we measure these things. There are some brown dwarf archives, but um, I wouldn't say as comprehensive as the NASA Exoplanet Archive, but it's certainly all public information. So if
Yeah.
people are really interested in diving into the literature and learning about brown dwarfs, then they absolutely can. We do have large catalogs of data that we use to do our work, and that we, have all of these properties that are listed that are very important to carry out these observations. Some of it's not very digestible in a non-expert way, but the NASA Exoplanet Archive, I think, speaks very nicely to both technical and non-technical audiences if you're interested to learn more.
Yeah, that's fascinating. I'd like to talk a little bit about, I guess, the technology and the data collection process for the telescopes.
Yeah.
So you've mentioned this, downloading data. What kinds of data are you actually collecting from Hubble and from Webb? And also, like, what is the size of that data? How much data are we talking about? And how do you process it?
Yeah, so the data there's like two forms of types of data that we're interested in. There's like imaging and then there's spectroscopy. So imaging is just collecting as many photons as we can from a given object and is much more easier to think about conceptually. So much like you have a CCD camera on your smartphone, it's basically like that. We have a CCD on a detector and that collects all those photons and then relates to a 2D image that we can see and we can interpret.
Okay.
Spectroscopy is a little bit more complicated because we're basically dispersing the light. So much like the famous prism experiment, if you put white light through a prism and then it disperses out into like a rainbow, then that is the spectra of light that we're
Oh,
seeing. And so we use elements like optical elements like that to disperse the light. And then we can collect that dispersed light that tells us information about the different wavelengths of light that we're seeing. So it's complementary to imaging. Sometimes we get both imaging and spectroscopy, because spectroscopy can tell us things like what components we're seeing within that data. For example, like molecules in an atmosphere of an exoplanet, whereas imaging will tell us more about the sort of position on the sky and the color of that object and what it is we're looking at. So those are the kind of two main pillars of the types of data that we get. In terms of the volume of data, I mean, it's huge. Like,
yeah,
I don't know how many terabytes or more. Like, I don't know. I can put a number on that.
yeah.
The Roman Space Telescope that's due to launch later this year is going to have an even larger volume of data than anything we've been dealing with James Webb and Hubble. And it all resides on our sort of internal archive that anyone can
Oh,
access from all over the world. So scientists who use this archival data to carry out their research. So it's not just taking new data all the time, but actually going back and looking at some of the archival data to do research. So all exists on these huge drives that we have in an archive that are stored.
wow.
That's part of what we do as well at the Space Telescope Science Institute.
Wow. You mentioned analyzing data. You mentioned writing code as well. Like, what types of analysis are you doing with the data? And also, are you using AI, machine learning to process the data? Can you talk about that a little bit?
Yeah, absolutely. So the analysis of the data, it depends what type of data we're looking at. So the imaging data analysis might look quite different to the spectroscopic data
Yeah.
analysis. I do a lot of spectroscopic data analysis. So for example, we have different models of different atmospheres of exoplanets that have like known physics baked into those models. So we say like, for example, if we expect carbon dioxide in this atmosphere, we would expect to see this feature in this spectrum. And if we do or don't see it, compared to our data, compared to the model, if we compare the data and the model, then that
Hmm.
tells us a piece of information that might tell us there is carbon dioxide there or there isn't. And we can do this with lots of different molecules. And that is like one way that we sort of analyze the data. Imaging, one of the things that I get excited about for imaging is using the position of a planet in the sky relative to its star. And this can tell us the orbital information of that planet, for example. And so we can
Oh.
fit the orbit analysis over time using the images and actually map out where the planet is going relative to its star. And then
Hmm.
that can tell us information like the mass of the planet, because that impacts the orbit. So there's a lot of different analysis that we can do. That's very biased towards what I do in my own research. If you ask someone who worked in a different area of astrophysics, they would answer differently, I'm sure. But those
Mm.
are some of the main things that I do. In terms of AI and machine learning, and I'm going to keep mentioning the Roman Space Telescope here, because this is, I think, going to change a lot of the way that we think about
Mm.
data volume and how we analyze large data sets. Is I think AI and machine learning is going to come into play a huge amount here because we're about to receive this tidal wave of data that we're not going to be able to just sit down and sort of intricately analyze one by one. So kind of like you mentioned before, having this more automated way of looking at things, I think this is when it's going to really like come into effect. And there's definitely people who are pioneering the field, who are very interested in using AI to be able to do that across a comprehensive data set. I'll say it's not something that I'm really using in my data because I'm very much looking at data set by data set because of the nature of what I'm doing. But I think
Mm.
people who are interested in more like larger field, looking at lots of different galaxies at once, for example, have a very different mindset in how they're looking at this data. And so I think it's definitely going to come into play. And I think we're going to see a shift in how AI is used in the field of astronomy in the next few years.
Wow. That's amazing. So I'm interested in the NASA Jet Propulsion Laboratory Mission Design School.
Mhm.
So what is that? So you completed that program. What is this training program?
Yeah, so the Astrophysics Mission Design School is a program that's open to astronomers at a career stage where um, they already have their PhD or they're close to getting their PhD, and
Okay.
they're sort of in their early career stages. And it's basically learning how missions are designed, like how we go from a concept and trying to answer a scientific idea to actually generating that into a mission that could be launched and try to answer some of those questions. So it's going through the entire process. You work closely with what's called Team X, who are the engineering team based at JPL. So that's in Pasadena, California. And you work closely with them to do what's concurrent design engineering. And so you have scientists who will say, I have this question that I'd like to try and answer. I need this specific thing like this spectral resolution, this angular resolution in order to answer that question. An engineer will come back and say, okay, I can give you this resolution, but it's going to be too tricky to do maybe this thing, but we can give you this thing. And you kind of like iterate on this process where like within the technological capabilities of what we can do, given those constraints, what can we answer scientifically? And it's a bit of
Mm,
a back and forth, like scientists approach things with a different hat on than engineers do. And being together in that room, working directly with the engineers, is a really important process to really understand what we can build and what we can design. And then there's other aspects related to it, like how do you weigh up the costs and risks associated with a specific mission?
mm.
How do you manage that mission? I was the project manager for this particular program. And so, how do you put all of those moving parts together to make sure that you have a successful concept? And then at the end of it all, you have this large proposal that you put forward to NASA, and you basically stand at the front of a room and you give a very long presentation that says, hey, this is a thing that we would like to do. And you answer a lot of questions, and it's a very rigorous process, but it's also you learn a lot. It's very interesting, and I really did gain a lot out of that experience.
When you say mission, what does mission mean in this context? When I hear mission, I think somebody going into space. That's not really what this means, right? Like mission is like a study,
Yeah, mission is just like sending anything into space, really.
anything.
So
Okay,
it could be a crewed mission. So that would be when we actually send humans on board.
right.
But an uncrewed mission is much more common. Like we have many missions that are um, satellites or telescopes that are never going to have astronauts associated with them, but they're just us sending spacecraft to different places in space. And yeah, and the mission is kind of answering a question. Like we're sending that spacecraft for a reason. Like we're not just sending it for fun, we're sending it because we want to try and answer a question. And so the mission would be deemed successful if you launch that thing and then you were able to use the information from that to help answer a question that you may have.
Does mission always mean building some new piece of technology, like a new telescope that's going to go into space, or not necessarily? Like you could utilize Hubble or something like that for a mission.
Yeah, so yeah, some missions use existing technology.
Yeah.
We have things called like technology readiness levels, and so that can sort of
Mm.
dictate um, whether we need new technology or whether it's technology that
Oh,
we can kind of buy off the shelf, sort of like commercial grade things that already exist and we already know work
right.
successfully, and we can basically just buy those things, put it in a rocket and launch it. And that would be a much cheaper mission than something that has brand new technology that needs to be developed in a lab or by engineers before we can even launch it. And so there are different grades of technology level readiness that we can sort of hit. Usually it's a mixture. Usually there's some technologies that are very well tested, and then there are some technologies that we're trying out and that we're demonstrating for the first time. Um, and then there are missions that sort of come off of the back of other things that already exist. So the
Mm.
International Space Station, for example, we may send astronauts there. There's always astronauts at the International Space Station, but there might be an astronaut that is specifically sent to work on something at the International Space Station, which would be deemed a mission to answer a specific question. So using the microgravity environment there, they may want to answer a question about how the human body responds to that, for example. And that could be deemed a mission in itself without developing any sort of new launch technology, because
I
we're
see.
sending an astronaut in a well-defined rocket that we know how it interacts with the International Space Station, but we're learning new information in a different way. We also have like small detectors on board the International Space Station, which are almost used like mini telescopes in a way. And so we don't necessarily need to send a whole new structure up into space, but we send an astronaut who could install
Oh,
something on a smaller scale that we
I
can then
see.
use. Yeah.
So interesting. In terms of your career path, you studied astronomy and astrophysics. What's the difference?
Um, yeah, so what is the difference between astronomy and astrophysics? Depends who you ask, really. So I think the way I sort of think about it is astronomy is a sort of like observational component of understanding like what it is that we're looking at in the night sky. I think astrophysics is more actually deep diving into the physical processes that underlie those
Mhm.
astronomical things that we're seeing. So it's kind of the difference between saying astronomy is like looking up at the night sky and seeing a star, and then astrophysics is saying, okay, how do we understand the physics of that star that we're seeing?
Oh,
And
wow.
so those two things are very complementary in nature, and
Mm.
like depending on who you ask, they might describe themselves as an astronomer or an astrophysics, but really there's a very blurred line between the two of them. And sometimes I'll introduce myself one way or the other. But
Oh,
there's a lot of overlap, yes.
when did you become interested in studying space?
Yeah, so I think since I was really a child, like I had this
Yeah.
really wild dream when I was like 5 or 6 years old that like the universe was just expanding rapidly, and
Right.
I really like freaked out and I wanted to understand why. And I think since that like very young age, I just had this real fascination with how the world around us works. And
Right.
um, when I was young, I had this small telescope that my dad had bought me, and I grew up in the south of England, and we used to go up to the South Downs, and we would look up at the night sky and try and look at the moon and
Mm.
Jupiter's moons, and just kind of understand like what it is we're looking at, and just having this fascination with the way the world around us works and interacts,
Mhm.
and what the underlying physics is. And so I think from a very young age, I was just always interested. And then I think as I then went into university and I was thinking about university options when I was like 16, 17 years old or so, that really sort of kickstarted the wow, like I really actually want to go down this path of astrophysics and learn more.
Mm.
So it's really hard to define like an exact moment, but
Right.
I've definitely always had that fascination.
Did you ever want to be an astronaut and go into space?
Oh, I still want to be an astronaut. I
Oh,
mean,
okay.
if the opportunity arises, maybe I'll go. We'll see.
So what
Yeah.
is that? Is that just a completely different path?
So a lot of astronauts are will train in a different sort of area that then becomes complementary to becoming an astronaut. So
Oh,
um so some astronauts might be astrophysicists that turn into astronauts.
right.
A lot of astronauts have military backgrounds, so helicopter pilots is seems to be a popular one. And we need good pilots to be astronauts. And medical doctors, there's a lot of like medical unanswered questions that we want to answer in space, so they might become astronauts. There are many different pathways to becoming an astronaut. And
Mm.
so any sort of strong background in science, technology, engineering, medicine, or like pilot background, being in the military, that kind of thing, could send you on a path of being an astronaut. So they usually, if you look up the history of any astronaut or any career path of any astronaut, they would have had a whole other career before they then turned into an astronaut. And many astronauts
Right.
sort of make the transition. I don't want to say later in life that they're old, but sort of like maybe in their 30s
Right.
and 40s when they've already developed a career in a given area and become an expert in that thing, and then using those skills to then like take it into space, essentially.
There would be a clear path for you if you wanted to be an astronaut. I'm not saying easily get there, but you could get there. Like there's a path.
Yeah, and I always apply whenever there's an open round where they're looking for new
Oh.
astronauts. But it's just a very competitive process, as you can imagine.
Oh.
So I'm certainly qualified to on paper, but then the actual getting to that interview stage and then processing further than that is just extremely competitive.
What are you actually applying for it? To be an astronaut or to enter some kind of training program to be an astronaut?
I mean, those things are basically the same because
Okay.
once you've done the training, you are then classified as an astronaut. Whether or not you
Right.
go to space is a different question. So you
Right.
could go through the sort of basic training of what's
Oh.
required to be an astronaut, and then often what happens is they'll sort of be sitting waiting for a mission to be assigned to them. And so some
Oh.
people may train as astronauts but actually never go into space. But they'd still be called an astronaut. But
Oh,
then there are
interesting.
some people obviously that then get assigned to missions and are able to go into space. So we also have like reserve astronauts as well who go through the like basic training, and they probably wouldn't be the first choice of person to be sent for a specific mission, but you want to have a sort of back pool of qualified candidates who, if we needed them, we could send them. So yeah, it really is about going through that training, and then at the end of that, you sort of officially qualify as an astronaut. But a lot of them, I think, still have duties in their chosen careers and
Yeah.
are still affiliated with that, and they have continuous ongoing training as well. So it's not like, oh, the training stops and then that's it. It's like it's continuous, and they keep learning and they keep doing different things. But the actual amount of time they spend in space is quite limited. It's even if they do go on a mission, it might not be for a long period of time. There are some astronauts that go for long periods of time, but that's not always the case.
Sounds like there could be a lot of astronauts that are waiting for that call.
Yeah, absolutely.
What skills matter most for students interested in space science today?
Yeah, so I think there's many skills, right? Coding is a really important one that is becoming increasingly important. I think we're seeing more and more young people at younger ages who are getting more fluent in different coding languages. And we do a lot of coding in Python, but there are many different coding languages we use. So I think building up that base in coding, it puts you at a real advantage. But any kind of like analytical skills, math's really important. Like a lot of what we do is, based on fundamental principles of math and all the physical laws that reside under that. But then those are like the more technical, sort of harder skills. But then the other skills that are often forgotten about are things like communication and teamwork. There's this perception that a lot of academics and people that work in this field kind of sit in a closed office and don't really interact with many people, and that is just so untrue. What we do is we work in large teams to be able to answer these questions and to be able to interact with many different people is super important, and communicate between team members, but also communicate to stakeholders who provide our funding or to members of the public, like things like doing this podcast. It's very important to be able to actually communicate what it is we're doing. Because if we do all of this research and we don't actually communicate that, then what was the point of doing the research? So I think you've got to build up a diverse set of skills. And don't put too much emphasis on just one of those, but lots of different aspects that bring you together and would make you a successful scientist.
What will we likely know in 10 years that we don't know now?
That's a great question.
It's a long time too. 10 years is a long time.
It both is and it isn't. It's weird on like astronomical timescales of like what you can and can't learn. But like in 10 years from now, I hope we have a better understanding of the amount of Earth-like planets that exists in the universe, or at least within our galaxy. I could keep mentioning the Roman Space Telescope is going to be the next big player in the field, and I think over the next few years, once we get that huge increase in the number of exoplanets that we detect, will hopefully help us answer how many Earths we expect to be able to find. So not just planets, but how many Earth-like planets. I think that's achievable on the 10-year timescale. I'm not sure. Like the next big thing I would like to answer is finding signs of life on those planets.
Yeah.
But I don't think that's going to happen in the next 10 years. I would love to be proven wrong.
If you detected life on a planet like tomorrow, what would be the next steps? Like, what would be the immediate next steps and process? Like, oh, we think there's life on this exoplanet. What would be the next step?
Yeah, so I mean, we would have to get this very much verified. It would take a very rigorous process of many people looking at the data and analyzing it to make sure that what we're seeing is that we're confident that it is signs of life and it's not something else. So I think there would be many people involved in that. If we were confident in that, then it would involve writing a paper that would be submitted and hopefully published in a peer-reviewed scientific journal. And that process would also be very rigorous. We'd have external referees looking at that paper to really, break down every possible argument that it could or could not be signs of life. Have to be very clear when we publish things, like what it is that we're looking at, and to not publish something that is inaccurate or misleading. If that paper then got to the point where everyone involved in that process is happy and confident that what we're seeing is indeed signs of life, Then
Yeah.
um then we would do a big press release. That
Right.
would definitely be worthy of doing a press release.
Yeah.
So big space agencies like NASA and ESA, who I work for, and others would probably do a massive press release to the public to say,
Yeah.
we found this thing. I mean, that would be a game changer. And then off the back of that, I'm sure there would be many journalists and people who would then run a lot of articles on something like that. It would then lead to a lot of other scientists, a lot of other astronomers who would want to follow that up to take more data to, verify what it is we're seeing. Um, but we have to be very cautious with how we do this like level of scientific investigation and what the
Right.
results and output of that are, especially for something that would be so huge and really game changing.
Yeah. If you could point the James Webb Space Telescope anywhere, what would you look at?
Oh wow.
One direction for a really long time?
I mean, I would love for there to be an even deeper version of the deep fields that we already have. It's not really my science, but I think it's fundamentally interesting from the perspective for sort of everyone to truly understand the scale of the things we're looking at. So I think kind of like what we said before, if you could just take the James Webb Space Telescope and stare into a patch of maybe what
Yeah.
looks like black darkness just from the human eye, but just to stare at that patch of sky for like maybe even months, I mean, that would be actually logistically impossible. But if we could do that, that would be amazing because then we would really be able to get a version of the deep field that's even deeper than what we have.
Wow.
Yeah.
That's a great study. You need a dedicated telescope to just look in one direction for a year.
We can write a proposal to
I'm
NASA to get
I-
them to do
I'm going to
it.
write a proposal. I'll write. You said anybody can apply, so I'm going to write a proposal.
Yes.
Okay, you ready for the lightning round? These are like quick questions, 30 seconds each.
Okay, I will try and be quick.
What do you think of astrology?
I think it's an interesting ancient concept that has great historical roots, and I think it connects us to that people have been looking at the night sky for a very long time to try and understand our human interaction and connection to what we're seeing in the night sky.
Sure. Good answer. What's the most mind-blowing fact about the universe?
That it didn't exist at one moment in time, and now it
Yeah,
does for the
yeah,
past almost 14 billion years. Like,
yeah.
where did it come from? I mean, that's just mind blowing.
A space myth you wish people would stop repeating.
Okay, gravity exists everywhere. Just if you go up to the International Space Station, gravity still exists there. It might be microgravity, and the effects on your body will be different, but it's
Right.
not a no gravity environment. It's just a low gravity environment.
The most beautiful image ever taken by a telescope.
The Hubble Deep Field. We've spoken
Yeah.
about it a lot, but just to see the sheer number of galaxies that we weren't able to previously see is just incredible, and to see the diversity of them as well.
I'm looking at them right now. I found some. These look like they're AI generated, but they're not. I'm sorry.
This was taken way before AI
Yeah.
was a thing.
One exoplanet you'd love to visit.
Oh, um, everyone gets really excited about the TRAPPIST-1 planets, which has many planets in that system. TRAPPIST-1 is the name of the star. And to understand if there's an atmosphere on one of the planets, TRAPPIST-1e is one of the ones that we've been investigating a lot. And so
Mm.
I would like to go there just to see if it has an atmosphere, because it's one of our outstanding questions in the field of exoplanets.
For these exoplanets, do you have images like up close of the exoplanet, like the surface?
No, not the surface.
Okay.
We do have images, but it's very complicated to get images of planets. It's what I do, but it's very hard
Yeah.
optically to do it. And so we have like you would see it as like a bundle of pixels on an image. It doesn't look very exciting,
Oh,
like
wow.
the human eye. We don't have the level of detail that we can get from like solar system planetary imaging. So you can see like surfaces of Jupiter and even Pluto.
Yeah.
We've sent probes out there to take images, but you'd have to get really, really close to be able to get that level of detail. And these things are very far away from us.
Is that something we would see in the next 10 years, the ability to take close images of an exoplanet?
I wouldn't say so because the angular resolution that you would need to do that would be absurd.
Mm.
Yeah. And it's
Okay.
not coming in the next 10 years. These missions take decades to build.
If you weren't an astronomer, what would you be?
A professional runner.
Oh, okay. It's different. A book, science or fiction that shaped how you think about space.
I love this series of books from Professor Brian Cox, who is a famous British astrophysicist.
Hmm.
Books called Wonders of the Universe, Wonders of the Solar System, Wonders of Life. And they kind of all came out around my time in like high school, where I was like
Hmm.
getting especially excited and interested about astrophysics. And they're very digestible reads. So if you're like interested in learning more about astrophysics, but don't want something that's so heavy,
Right.
then I really enjoy those books.
Cool. What's your favorite band right now?
Fontaines DC. They're an Irish rock band. I saw them first a few years ago. They were supporting the Arctic Monkeys at Red Rocks in Colorado, and they were amazing. And I think they've been my top band that I've been listening to on Spotify for the past couple of years. So they're
Oh
really
yeah, I've seen these guys. I've seen pictures
yeah,
of these guys
they're
before.
really
Yeah,
great.
I'll check them out. Well, thank you very much. This was great. Thanks a lot. I really appreciate it. Nice meeting you.
Yeah, likewise. Thank you so much for connecting and making this happen.
I'll be in touch in the next few days.
Okay, sounds great.
All right.
All right.
Have a good day.
You too. Bye.
Thanks for watching. If you like this, be sure to subscribe. More interviews and demos coming soon.